Hi! In today's video, I want to introduce you to the remote processor subsystem in Linux. In modern chips or ASICs, you normally have something like this. So this here is a block diagram of the AM625 chip from Texas Instruments. And here we can see we have application cores, which are normally used for running the operating system like Linux, for example. But for real-time relevant tasks, you also have a second processor embedded into this chip, which can handle those tasks. So here we have an ARM Cortex M4 core for doing so. And the remote processor subsystem in Linux offers us control from Linux to this embedded processor. But for keeping it a little bit more simple, you can see my setup here. So basically I am having here a BeagleBone Green board. This board actually has some subprocessors, but for keeping it more simple and as there are already drivers written for them, I've connected an tiny 8-bit microcontroller to it. And here is the reset pin, which is connected to a GPIO of my BeagleBone. And when I pull this pin low, the processor will stay in reset, and when I pull this pin high, the processor will start executing code. And I think this is a very simple example, but I think it's enough for explaining the most relevant things of the remote processor subsystem on Linux. Okay, so let me connect to my BeagleBone Green. Here we are, and I've already prepared a little thing so I can speed everything up. So here in this folder I have a makefile for building our driver, I have a source file for our driver, and I have a device tree source file containing a device tree overlay to add our remote processor here. And I've already compiled this to a DTBO file. So let's take a look at the device tree overlay I'm using here. So this is a device tree overlay. We are adding one device to the root path of the device tree. So here we're adding the device rproc, and this device is compatible with a driver with the compatible string rproc. The status is okay to enable the device, and I'm using one GPIO pin for the reset functionality, and this GPIO I'm using is from GPIO 0 pin 20. And that's basically all we can see here. So I've compiled the device tree overlay and I've added it to my U-boot environment. So this device tree overlay is loaded automatically when booting. And if I take a look at device tree here, I have the device rproc available with my reset pin, the name, the status, and the compatible string. For example, if we take a look at the compatible string here, yes, this is exactly my rproc, which you would expect. Okay, so let's take a look at the template which I will use for the driver. So I've already shown you how to parse devices from the device tree, and if you're interested in that, I will put links to these videos in the description down below. So here, basically, we are declaring a driver for a device, tree device. Therefore, I have to set the IDs or the compatible strings my device will be compatible with, and here we can see this is exactly the same string we have seen in the device tree overlay, so rproc. And here I'm creating an object from the type struct platform driver, and I'm naming it rproc driver, and here I have a pointer to a probe and a remove function, and also the link to the ID lists or to the compatible lists, so the driver knows with which devices it's compatible with. Down here I'm using the macro module platform driver to create me the init and the exit function for this driver, and in these init and exit function it will register this platform driver I've defined up here. Okay, and now my job is to actually implement everything I need for the remote processor subsystem, and my goal is I want to be able to start the tiny and stop it. Yeah, so let me show you how to do this. But first I need two more defines. The first define is remote processor, and the second one is linux/firmware.h, because over this remote processor subsystem we can also download firmware to a processor. And the first thing I will do is I will create a new struct. I will call my rproc, and the struct contains just the GPIO, for which I will name reset pin. Yeah, and that's everything I need in here. Okay, then I will create a new object from the type struct rproc operations, and here I can set all the operations which should be supported by our remote processor, and I will call it my rproc operations. And what I want to do is I want to implement a start function, which is called when I'm starting the processor, and I want to name it my rproc start. Then I want to implement a stop function, which I will call my rproc stop, and I want to implement a load function, which is executed when firmware is downloaded. Of course, as I don't have any any way to transfer data here to my processor, I won't actually load firmware, but I want to show you how this function or callback function would look like. Okay, so next thing I have to do is I have to implement these. Or first, let's start maybe with the probe function here. Then here I will need some additional arguments. So I will declare a variable or an object from the type struct my rproc, and I will declare a pointer of the type rproc, and I will also name it rproc. So this is actually our remote processor we want to add. And the first thing I will do is I have to allocate memory for a new remote processor, and I can do so by calling the function rproc alloc. And this function needs the following arguments. The first one is a pointer to a device to which the remote processor is connected, and here I will be using my platform device I've set up in the device tree. The next argument is the name. Here I will use my rproc. The next argument is a pointer to the rproc operations. The next one is the default string of the firmware I want to load. And here I will use my rproc firmware. I could even say my rproc firmware.bin or .elf, depending on what file I want to load. But here I will just name it my rproc firmware. And the last argument is, with this allocate command, I can also allocate the private data for my remote processor. And here I have to specify the size of this private data. And this is just this my rproc string here. So I will allocate so many bytes for the private data. Okay, after this is done, I have to check if I got a null pointer returned here, because if so, error allocating rproc, I got an error, and I will return error no memory. Okay. Then the next thing I want to do is I want to have my private data in this ddata object. So I can do so by accessing the private data this way, and then I will set up my reset pin. So ddata reset pin is gpiod get. So the first name is again the device in which we can find our GPIO. The second one is the label, which was reset. Maybe let's check what it actually was. Yeah, reset pin under -GPIO. So I have to name it reset -pin here. Reset pin. And the last argument is how I want to set up my GPIO. And I will use GPIOD out low here. Then I have to check if the pointer which was returned is a valid pointer. And in case an error occurred, let me copy these 3 lines. Error, setting up, reset pin. Then of course I have to delete my remote processor which I've allocated here, and the last thing is I will return the error, which is pointer error, data reset pin. Okay, but if we are down here, we have successfully set up our reset pin. Good. Now the last 2 things I will do is I will set the platform driver data, so we can have it available in the remove function as well. And I want to set the driver data of my platform device pdef, and I want to set it to rproc. And then I will call the function rproc add, which will actually add our remote processor. And here I have to pass in a pointer to the remote processor I want to add. And in case status is not equal to 0, an error occurred. So let me copy these 2 lines here. So I will error adding my rproc. So I will delete it, but first I will free my GPIOD with GPIOD put, and then reset pin. Yeah, here we go. And down here I'm returning the status, so if this was successful, the status will be 0. If not, the error code will be stored in here. Okay, and in the remove function I can copy a lot of stuff. So let me copy it. And I need the 2 variables here. So the first thing I will do is here I will call the function platform get driver data to get the driver data again. Then here I'm setting the I'm getting the private data out of my remote processor. Down here I'm freeing my GPIO pin, and down here I'm deleting my remote processor. And that's it. That's everything we have to do in remove. Okay, so the last thing which remains is I have to implement these callback functions here. So let's do this. The return value is always an integer, 0 on success, error code else. And let's start with this start function. The argument here is from the type struct rproc. So this is just a pointer to our current remote processor. So basically I can copy this line here, and I will set the data to rproc priv. Then I will print something out to the kernel's log. So I will print out my rproc starting a tiny. And then I have to set the GPIO pin with GPIOD set value, the data reset pin this here, and I want to set it to 1. So I am asserting the reset, and now the processor should be running, and then I will return 0. So the stop function looks quite similar. The arguments are the same. I'm still having a pointer to my remote processor, but now I want to stop a tiny, and I will set the pin to 0. And the last function I want to implement is the load function. So this function is loaded whenever I want to load the code to my processor. And here the second argument is from the type construct firmware, and it's a pointer to my firmware. And here I will just print out 2 lines to the kernel's log. So I will print out my rproc loading the bytes of firmware. And here, so here this firmware struct has a field called size, which will give us the size of the firmware in bytes. And if we want to access the content of the firmware, we can use the data field here. But maybe it's wise here to convert it to char star. So I will just use text files for the firmware because I can't actually load something to my atiny. This should just demonstrate how the loading process is working here. Yeah. Okay, so that should be it. Let me try to compile it, but I'm quite sure I made some errors. The sad thing is the BeagleBone Green has only a single core CPU, which is also quite old now, so compiling will take some time. Okay. Yeah, here I forgot the braces. data reset pin. Okay, let's take a closer look at it. Struct GPIO. Oh yeah, this D. So first thing I have to do is I have to delete this D. The struct is called GPIO desk, not GPIO D descriptor. Then the next thing, what is wrong here is this conversion. Of course, for the conversion I need braces. Okay, so let me try to compile it a second time. Okay, oh yeah, I forgot to return something, so let me fix this as well. So the load function has also an integer value here, and I have to return a 0 here. So normally here in the load function you would copy your firmware to the right destinations, and if you're having an ELF file you would transfer, or you would check which sections are available and then copying everything over to the right memory regions. Yeah, but as I already said, in my case it's a lot simpler. So let's build it a last time so we shouldn't get any warnings and no errors, and then we can try test it. Okay, this is looking good. Then I will fire up tmux and open a second window here. So here I want to follow the kernels log so we can see it here. And here I will execute sudo insmod my rproc.ko. Okay, and we see we have loaded a module here, and my rproc is available, but the direct firmware load for my proc firmware failed with error -2. Okay, so it couldn't load the firmware. But first let's take a look where we can interface the remote processor now. So if we go to sys class remote processor, we can find all the remote processors which are available. And as I already told you, the chip used on the BeagleBone has some real embedded processors which we can control over these 3 remote processors interfaces. But I want to navigate into the free here, which is my remote processor. So in here we have a bunch of files. For example, we have a name file. So let's take a look at it. So the name is my rproc, which we mentioned. Let's take a look at the firmware name. And the name here is my rproc firmware. And here we have a state. So over the current state, we know what state the processor is in. Currently it's offline. And so where can we place the firmware? So basically there is a folder in lib firmware, and from this folder, it's parsing for firmware. So now let me change to root user, then I will echo this is the firmware of my rproc, and I will write this to lib firmware and then get the name because I already forgot it. And now if I take a look at lib firmware, we have not name firmware. Yeah, okay, let me do it one more time. Sorry for the fuss. This is firmware, not name. And now we should have a lib lib firmware a file called my rproc firmware, which contains the firmware for processor. And now if I want to start my processor, all I have to do is I have to write start into this file. And let me turn on the webcam again. This is a little bit bad. This is better so we can see what's going on in the kernel log. If I'm doing this, state not start, sorry for this. Okay, we are loading 33 bytes of firmware. So first the load function is called, and this is a firmware for my proc, so here I'm printing it out. And then I'm starting my atiny, and here you can see now the LED is blinking, so the core is actually running. And if I cat the state of my remote processor, we can see it's now the state running, so it's actually running. And if I write a stop to the state, okay, now the processor is stopped. Hey, this is really cool. So over this remote processor subsystem, I can start and stop remote processors, and I can even download firmware to it by writing the file name into this firmware file. Pretty cool, isn't it? Yeah, okay, so I guess that's it for today. I hope you've enjoyed the video and learned something. In case you want to support my work, you can buy me a coffee on buymeacoffee.com/Linux. So thanks for watching and goodbye.